recording. Okay, we're in section 6.6. We're talking about applications to physics and engineering. And we talked last time about how the work, the work is generally equal to the interval from A to B of your force function. Okay, that's a general formula that we derived, and there's a lot of situations that involve work. Okay, it could be the stretching of a spring. It could be raising a cable to the top of a building. It could be pumping water out of a tank. A lot of applications, and I want to look at a few problems here today from section 6.6. So let me give you a moment to copy down this example, and then we'll discuss its solution. Okay. So very good. Let me know if you have any questions. Okay, so let's take a look at this problem here. Let's take a look at this problem. So in this problem, we have a 1,600-pound elevator. 1,600-pound elevator that is suspended by a 200-foot cable that weighs 10 pounds per foot. Okay, so, and we're being asked how much work is required to raise this elevator from the basement to the third floor, a distance of 30 feet. So recall in the last class, last Thursday's class, from section 6.6, we looked at example 3 from the textbook that dealt with work needed to lift a cable up to the top of a building. This problem is a little more complicated because we have the cable, and we have an elevator. And we're going to be moving, in order to move that elevator 30 feet, we have to, of course, move the elevator 30 feet, but then I have to winch up 30 feet of cable as well. So it's a little bit more involved problem than the book problem, but nevertheless, in your homework for section 6.6, you have problems with where you're pulling weights up, so forth. So what do you think would be a good approach to start this problem off? what would be a good approach that will help kind of orient you correctly on the problem? I agree, Tosh. We need to draw a picture. And on the next page, the solution, I have a picture drawn. And there's a lot of writing here. So what I want to do, I want to kind of take it step by step. First thing I want to let you do is draw this picture. Okay. Draw this picture. And then I'll discuss the work that the notes that you're going to see here. So take a moment to draw the picture. Okay, so there's the, we have this cable, and let me see, maybe I will put it in red. We have this cable hanging down here, all right? And the elevator is, at the bottom. Okay, so in other words, the elevator's at the bottom in the basement, okay? And we want to move the elevator up 30 feet. So, all right. The total work, let's first of all focus on, hold on here, on the elevator, So the elevator, you're raising the elevator 30 feet. Okay, so that just means the elevator gets moved 30 feet. How's work defined again? How's work defined? I mean, I'm not talking about the integral, but what's like the simple definition of work? Work equals
force times displacement.
That's right, Ange. Force times distance. So here you have a force of 600 pounds and a distance of 30 feet. Okay, you don't need to worry about acceleration due to gravity because the units, the pounds is already a unit of force. So this is the component of the work where you move the elevator. Now you have to worry about the cable. So in other words, for the elevator to move 30 feet up, the cable has to also move 30 feet up. Well, how long is the cable again? How many feet are in the cable? How long's the cable? How many feet?
200
That's
feet.
right, 200 feet. 200 feet. So the thing is, you have this cable. Maybe I'll just draw the cable right here. You have the cable, and what I'm doing is I'm taking the cable and splitting it into the bottom 170 feet of cable and the top 30 feet of cable. Okay. So when we move the elevator up 30 feet, does the bottom 170 feet of cable, does it ever reach the top of the building? The bottom 170 feet of cable? It does not. That's right, Javier. If the elevator moves 30 feet, the bottom 170 feet of cable just moves up 30 feet. Okay, it never reaches the top of the elevator. So I mean the top of the building. Sorry. So what I'm saying is the top of the building. Here's the top of the building. Okay. All right. Maybe I'll put that in purple. This is the top of the building. And when the elevator gets moved 30 feet up, the top 30 feet of cable reach the top of the building, but the bottom 170 feet of cable just get moved up 30 feet. So we can treat the bottom 170 feet of cable here like dead weight, just like the elevator. The bottom 170 feet of cable get moved 30 feet. But how much do the bottom 170 feet of cable weigh? Well, every foot of cable weighs 10 pounds. So if you're going to determine the work needed in moving the bottom 170 feet of cable 30 feet, you just take the force times distance. Well, distance is 30 feet, and the force would be 170 feet times 10 pounds per foot. Okay, that'll give you the weight, which is 1,700 pounds. So that takes care of the bottom 170 feet of cable. Now we have to worry about the top 30 feet of cable. So the top 30 feet of cable, again, when you look at it, you have to think about and I want to be a little careful how I draw this, but let's say, you have this piece of cable here, okay, we'll call that piece of cable X1, and then you have this piece of cable here that's delta X feet wide. Hold on, now wait. No, that's our second piece. Let me do this again. Let me just do this again. So, I mean, you have the picture here, and I've drawn, one moment. Yeah, I've drawn two pieces of cable. Okay, but really, let me just draw a new picture here. Let me just draw a little bit of a new picture. Okay, let me draw it over here on the right. Okay, so, and of course, maybe I'll go down here and draw the picture right here. So here's my 30 feet of cable. Okay, this here represents 30 feet of cable. And here's a piece of cable here, here's a piece of cable here. The length of this is 30 feet. So this is the top 30 feet of cable. Each piece of cable is delta X feet wide. I'm going to call this piece of cable cable piece 1, And I'm going to call this piece of cable, cable piece 2. Okay, so I have cable piece 1 and cable piece 2. Which piece of cable is going to take more work to bring to the top of the building? Cable piece 1 or cable piece 2? Both pieces of cable weigh the same. But which piece of cable, the piece of cable 1 or piece of cable 2, does it take more work to bring to the top of the building? Well, which piece of cable is okay? That's right, Tosh. That's right, Javier. The cable piece 1 is going to take more work to bring to the top of the building because it's further away. It's further away from the top here. Here's the top of the building. Cable piece 1 is further away from the top. So you can't treat the top 30 feet of cable like the bottom 170 feet of cable. The top 30 feet of cable is not treated like dead weight because that top 30 feet of cable, if you break that top 30 feet of cable up into little individual pieces, some pieces it's going to take less work to bring to the top of the building than other pieces. So what you have to do is you have to take into account, all right, well, how much does each piece of cable weigh? Well, that's not hard. Each piece of cable in the top 30 feet of cable is delta X feet wide, and the cable weighs 10 pounds per foot. So the weight of the ith piece of cable is 10 times delta X pounds, because the feet here simplify out, right? But, all right, how far do you have to move that piece of cable? Well, you're going to move that piece of cable xi feet. So moving the top 30 feet of piece of cable to the top of the building, you can think of it as like cutting up that top 30 feet piece of cable into separate little pieces and moving each little piece of cable to the top of the building. So you get a summation. If there are n pieces of cable, you get a summation. And this would be that portion of the work needed to move the top 30 feet of cable to the top of the building would be this portion of work. But it only applies to the top 30 feet of cable. And naturally, as you take that cable, that top 30 feet of cable, and slice it up into more and more smaller pieces, you know, n pieces, you're going to let n go to infinity. And then this Riemann sum here is going to become an integral. So are there any questions on how this problem works? Are there any questions on this? I've tried very hard to break the problem, you know, really put in a lot of detail in, you know, what's going on, you know. And how is it helpful that I include the units in like the steps here? See how like feet cancel? How many find the units to be helpful, a helpful thing to see in the problem? Okay, the units help you out a lot, Taj. Wonderful. Good, good. Okay, so, well, if there are there any questions before we move to the next page to get to the final answer? Are there any questions at all? Okay. Well, what's going to happen, of course, is this Riemann sum is going to become an integral. Okay, and and then of course the other two pieces of work, they're just computational. So the work is going to be the integral then of 10x dx from 0 to 30. It's 0 to 30 because the 0 here represents the piece of cable at the top of the building. Okay, that's already at the top. So the top 30 feet of cable, there's a piece of cable at the very top of the building. It's 0 feet from the top. So 0 is your bottom limit. And then the 30 represents the piece of cable, 30 feet from the top of the building. So that's how you get those limits. That's how you get those limits. Okay? Because x is measured from like downward. Okay? The axis x, okay, here. This is your axis. It represents your cable, right? It represents your cable. And then again, here's the top of the building. Okay, and so here at x equals 0, that piece of cable is like right near the top of the building. And then x equals 30, that piece of cable is 30 feet from the top of the building. So that's how we're getting those values. And the Riemann sum was 10 times xi times delta x. That was the function inside the Riemann sum, 10 times xi times delta x. That just becomes then 10x dx when you do your integral. And so it turns out that the amount of work is going to be 103,500 foot-pounds. That's going to be the amount of work. Okay, are there any questions on that? Give me a thumbs up if you're feeling reasonably comfortable with what you're seeing so far. Okay, Taj is good, and Joseph's good, wonderful. And you're going to have a chance to do another one in your homework. But I can promise you, if you're comfortable with this one, you'll be okay with what you see in your homework. Okay. Well, I know it might seem a little weird at first. It might seem a little weird at first, Javier. I think what we'll do. Let's do another problem here. Let's look at a tank problem. Okay, let's look at a tank problem. All of these work problems have sort of a similar. They have a similar. What's the word I'm looking for? They have a similar approach, so to speak, to finding the solution. All right, let's look at another problem here. Let's look at this problem here. Let's look at a tank problem. Now the book has a tank problem as well, example 4. This problem here is an additional problem to the book problem. So let me give you a moment to copy this example down. Copy the picture too. This blue, this shading here that you see, this shading, okay, here, represents a layer of water in the tank. Okay, but let me give you a moment to copy everything down, and then we will look at the solution. Okay, so in this problem, we have a tank that's full of water. And what we want to do is we want to find the work required to pump the water out of the spout. So the spout, of course, is right here. So for the water to come out of the spout, it has to reach the top of the tank. Okay, once water reaches the top of the tank, it gets sucked out of the spout. So it's exactly like the problem we just saw with the cable. Once a piece of, to move a cable, well, I mean, if you think about example 3 from the textbook, to move the entire cable up to the top of the building, means you got to bring each little piece of cable up to the top of the building. So what we're doing here is, how are we going to empty the water out of the spout? Okay, how do we try to come up with a way to solve this problem? Well, what we can do is, instead of considering all the water at once, let's consider the ith layer of water. Okay, let's consider this here, the ith layer, of water. And the ith layer of water, okay, I'm going to give it a height here. Maybe I'll put this like this. I'm going to give it a height of delta x. Okay, so that's this height right here. It's an ith layer of water. It's a thin layer of water, but it has a height to it. And I'm going to call this distance here distance A. Okay, I'm going to call that distance there distance A. So let me ask you, the ith layer of water, what would the ith layer of water, what shape would it be? What solid would it be? The ith layer of water in the tank. I mean, think about solids, right? You just learned about solids. Okay. The ith layer of water here, this blue ith layer of water, and I guess I could, you know, sort of, I mean, there's the ith layer. What does it resemble? What shape? Can anybody think what shape it resembles?
Is rectangle?
That's right, Ange. It's a rectangle with some width to it. So it's like a brick. Think of a brick of water. Okay, a brick of water, or it's not a cube, but it's a rectangular parallelepiped. It's like it's a brick of water. And what do you think is very important to find out about this brick of water in order to compute work? We need to know what about this brick, this ith layer of water. Okay, it looks like a brick of water. Okay, like a candy bar. Think of a candy bar. Like how many have seen like the Hershey's bar in the stores, Hershey's bar? Okay, we love Hershey bars, right? Hershey's chocolate bars. Okay, Taj has seen that. Think of like that shape. That's like a very thin brick, so to speak. So think of this Hershey's bar layer of water. What might be important to be able to find on that layer of water in order to find the work needed to bring that layer of water up to the top of the tank? What's very important to find?
The volume?
That's right. That's right, Ange. That's right, Mario. The volume of the ith layer of water. So we're going to treat this tank of water, we're going to treat that entire volume of water as a bunch of layers. And if we can find an expression for the work needed to bring the ith layer of water to the top of the tank, then by adding up all those work values, if we add up the work, the sum of the work values, each work value is to bring up the ith layer of water to the top of the tank, and you know, we would break this tank up into a bunch of layers, right? A bunch of layers. If we could find an expression to bring up each layer of water to the top of the tank, we could find the work. So volume's important, but we can't find what's the volume for a brick. What's the volume for like a brick? If we wanted to find the volume of a brick, okay, let me just hold on. One moment here. Or a box of water, a thin box of water. Length times width times height. That's right, Joseph. So here we know the, let me put it the right here. We know the width here. We know the width. That's 10. The height of the ith layer of water is delta x, but the question is, what's the length? What's the length A? Would the length A, so if I think about another layer of water here, a second layer of water, if I draw it in here, okay, this second layer of water, which is lower from the top and the further distance from the top than than that other blue layer of water, is the length for the layer of water going to vary depending on how far the layer of water is from the top of the tank? Will that vary? The width 10 doesn't vary. The height delta x doesn't vary. But depending on where the ith layer of water is, will it have a different length? It will, absolutely. So that's right, Tosh. The length will vary because of the shape of the container. So what we need to do is we need to figure out what this A value is. So I'm going to go to the next page. And I have here in the solution what I've drawn. What I've drawn is, and you want to take good notes on this. There's a problem like this in your homework. That's due Sunday. Problem like this in your homework, and there's no help me solve. There's no like videos, help aids on it. So I'm being your help aid here. What I did is I drew a picture of the side of the tank. Here's a picture of the side of the tank. And I'm going to, and I'm going to zoom in a little bit here. So there's the side of this tank. And the ith layer of water is here, has height delta x, and it's xi feet from the top of the tank. Well, since the tank is 6 feet high, this distance here would be 6 minus x sub I. Okay, and I need to find a way. I need to find an expression for this A. And we know A is going to be some function of x, the distance you are from the top of the tank. So what I do is I say, okay, well, I can treat this, I can use the concept of similar triangles. Similar triangles. So we have here a big right triangle, and we have here a smaller right triangle. See that? A big right triangle and a smaller right triangle. And again, this here is my ith layer of water. And what I've done here is I've written down the big right triangle and the smaller right triangle. And are these two triangles here, are they similar right triangles? Are they similar right triangles? They are. That's right, Mario. You can, I mean, they are. They definitely are. And that means then that the sides of those two right triangles are in proportion. So again, what I want to do is I want to solve for A. I want to find an expression for the length of the ith layer of water that's x feet below the top of the tank. So, okay, I can say then, well, okay, A is to 6 minus xi, that ratio, would be equal to the ratio of 12 over 6. Right? Because the sides are in proportion, so the ratios are equal to each other. How many recall learning this kind of thing in like geometry in high school? It's something that, or even maybe even in middle school, who knows? All right, Sandia remembers it. Certainly in high school, you learned about similar triangles in geometry, and here we go. Now we're using it. So A over 6 minus xi, x sub I, is equal to 12 over 6. It's equal to 12 over 6. And that means then that A over 6 minus xi would equal 2. That's right, Sandia. And so that means then that A would equal 2 times 6 minus xi, or A equals 12 minus 2xi. And now we have an expression. For the length A of the ith layer of water,
Professor.
where that layer of water is x or xi feet below, down from the top of the tank. Question, Ange?
Yes, please. how we determine xi? Why we took xi to be that portion?
Well, I mean, all I'm doing in the picture up here, is I'm just drawing a you know, layer of water, and I'm saying that layer of water is xi distance from the top of the tank. I don't know what xi is. I know xi is going to vary from 0 feet all the way down to 6 feet, because I have layers of water on the top all the way down to a layer of water on the bottom. But this here is just a general x value. It's a variable. It changes depending on where your layer of water is. Okay, is that? I mean, we're going to make use of that, right? We're going to make use of that. We need to find an expression for the volume of the ith layer of water. And now that we know what the length is, we know the length A of the ith layer of water is 12 minus 2 times xi. We know the height of the ith layer of water equals delta x, and we know the width of the ith layer of water is 10. And by the way, the units here are all feet. So if I want to get the volume of the ith layer of water, I'm just going to multiply these three quantities. And does that length times width times height? That's exactly right, Sandia.
So basically, xi is a variable. I mean, it's
yes
along the 6 feet part of the rectangle.
It's a variable that changes depending on what the ith layer of water is.
Okay.
But it'll go anywhere. Xi could take on any value from 0 feet to 6 feet. That's right.
Okay, thank you.
Okay, all right, sure. So all right, let's go to the next page. So now we're going to find the volume of the ith layer of water. So the volume of the ith layer of water is 10 times A times delta x. And if you don't mind, I'm going to write 10 as 10 feet. A is, of course, 12 minus 2 xi feet. And then we have delta x feet. And that's going to get me 120 minus 20 xi times delta x cubic feet. I think the units are helpful because it helps guide you in terms of, hey, am I approaching this problem the right way? Okay, so now we know how much. Are there any questions so far? Okay, and you can see that the volume of the ith layer of water is a function of this x sub I, which is the distance that the ith layer of water is from the top of the tank. And that would make sense. That would make perfect sense. Okay. Okay, now next we have to find the force of the ith layer of water. Okay, how heavy is the ith layer of water? Well, remember, we're told in the problem that water weighs 62.5 pounds per cubic foot. How many maybe learned that in another class? How many maybe knew that or have seen that? Okay, well, so, all right, Mario and everybody, it's your first time, that's fine, you know. So the force of the ith layer of water, the force of the ith layer of water, my units have to be in pounds. So what I'm going to do is I'm going to take my volume of the ith layer of water, which I computed here, and I'm going to multiply it by the weight of the weight of water, 62.5 pounds per 1 cubic foot. The cubic feet cancel out, and you're left with pounds. So the force, or the weight of the ith layer of water, it turns out, you know, I'm gonna take that 62.5 and I'm gonna multiply it by the 120 and by the 20. The force will be equal to 7,500 minus 1,250 xi times delta x pounds. Now we have the force of the ith layer of water. What I want, of course, to find is the work needed to bring the ith layer of water to the top of the tank. So since work, remember, is force times distance, well, I need to then consider the distance. Well, the distance to bring the distance that the ith layer of water is from the top of the tank is xi feet, right? It's xi feet. So I'm going to take that distance and multiply it by the force for the ith layer of water and multiply those together to get an expression for the work. So the work needed to bring the ith layer of water to the top of the tank, or to raise the ith layer of water to the top of the tank, that work would be equal to what you see right here, which is 7,500 xi. See, I got this xi, I have to distribute it to the 7,500 and the 1,250 xi. So that's going to get me the quantity 7,500 xi minus 1,250 xi squared times delta x foot-pounds. So you see how I love to carry these units. I love to carry the units with me because it helps confirm that, hey, it's like a double check on how I'm doing the problem. How many recall like using units in chemistry to help you? How many recall in chemistry using units in your computations, in your work to help you? Sure, Tosh remembers that, Jan remembers that. It isn't any different here. Why shouldn't we carry our units with us? So, okay, are there any, we're almost there. Are there any questions up to this part right here? Okay, well now we know the work needed to raise the ith layer of water to the top of the tank. So the total work then, okay, now we're you know, total work needed to lift the the total work to lift all the water to the top of the tank would be the sum of all the work values. These little W sub I work values each represent the work needed to bring the ith layer of water to the top of the tank. So if you take the entire volume of water and break it up into a bunch of layers, n layers, okay, and add those work values up, you'll get an approximation for the total work needed to lift the water to the top of the tank. But if you let n go to infinity, you will be able to find the exact work. And of course, the Riemann sum will turn into an integral. Okay, so I mean, if I put in like below here, I can put this in below. Summation 7,500 xi minus 1,250 xi squared delta x, right? Where I goes from 1 to n, and you take the limit of this, Riemann sum, that's going to then get you this integral here. See, all the problems, the approach is similar. All these work problems, the approach is similar. Take the cable and break it up into a bunch of little pieces. Take the volume of water and break it up into a bunch of little layers of water. Okay, it's the same kind of approach. And without calculus, we wouldn't be able to do these kinds of problems. But with calculus, it's amazing what we can do. Are there any questions up to this part here before I go to the next page? And I want to make sure I'm pacing myself well. Are there any questions at all? Okay, well, so now what we have to do is compute this integral. And incidentally, you see how this problem, you see how I broke it up into pieces. Okay, I mean, in order to tackle the problem, I work it step by step. I mean, you know, we didn't just get to this integral, you know, right away. We had to compute, we had to figure some things out. And certainly for your next exam, I would want to see the steps in your work, right? Those are important. Okay, well, let's compute this integral. So here's our integral. It's an easy integral to do. And in the end, you're going to get 45,000 foot-pounds. That's going to be the work needed. Let's see, Sandia. I'm looking at the antiderivative. So here's the thing. How did I get this 37,000? How did I get this term here? So the antiderivative of 7,500 is 7,500 times x squared over 2. Right, well, and 7,500 divided by 2, that's right, Sandia, 7,500 divided by 2 is 3,750. So we put in the 6 and the 0 and work it out. Sandia, you're okay with that? Excellent, excellent. Okay. How many think this is actually pretty cool? Pretty cool what you're learning here in, I mean, the fact that you can do this kind of problem. I mean, this is an engineer's problem, right? Yeah. Taj likes it. Ethan likes it. Very good. All right. I mean, this is engineering, right? What we're learning here. So, based on calculus. So, okay. What I want to do. I'm gonna. I mean, we're gonna have more material we're gonna cover here, but I want to give you a 15-minute break here, and I will make these new exercises active on 6.6. So let me go ahead and stop the recording. I think there are no more questions. All right, very good, very good.